Hello, everyone. We're going to go ahead and jump right in. Hi, and welcome to Making Retrieval Augmented Generation Better with our developer advocate, James Briggs. My name is Amanda Wagner. I am the Senior Community Manager at Pinecone, and we are thrilled to have you here today. If you're unfamiliar with Pinecone, one, we hope you walk away from this more familiar. And two, Pinecone is a vector database that makes it easy to build high-performance vector search applications. Now, before we dive in, we do have a few housekeeping rules. We say, number one, use the chat for chat. Say hello, tell us where you're coming from, let us know what you're building with Pinecone, and then we ask for you to place all questions in the Q&A portion of the Zoom. So you'll find that on your bottom screen towards the left. So chat for chat, questions for the Q&A portion of the Zoom. We like to reserve roughly 15 minutes at the end of every webinar to answer your questions. So this helps us stay organized and answer as many questions as possible. We also ask that you act respectfully, politely, and, all those behavioral things in the chat. And then if you've missed something, no worries. This event, it's being recorded. After the event, we will send out the event recording as well with a post-event survey. Let us know how we're doing. It takes 5 seconds and it helps us bring you guys bigger and better content. Have any questions after the event? Go ahead and ask them in our community forums that you can access through our website. Now, without further ado, I'm going to turn it over to the fabulous James Briggs. James?
Thanks, Amanda. So I will just share my screen. One moment. Yeah, I think. Okay, cool. You, I think, should be able to see. So we're going to talk about making or how we make retrieval work for LLMs. So a quick intro into LLMs and the sort of potential that we have with those, which is relatively big, I think, and I think most of us here know that. So LLMs are naturally at the center of this sort of AI hype at the moment, and we've seen that there are some GenAI tools like GitHub Copilot, which, quite frankly, has been helping people be a lot more productive. And even for myself, right, I've been using GitHub Copilot for a year or so, and the level of my productivity when writing code is just like so much greater than it was before. It's made like a huge difference. And then if you scale that across all developers everywhere, and then you consider that there are other AI tools out there, like the sort of up and coming Microsoft 365 Copilot, there is a pretty huge potential of AI to sort of help us be more productive and just do cooler things. So the what you can see on the screen right now, this is from Goldman Sachs, and this is in an article they titled "Generative AI Could Raise Global GDP by 7%." Now, maybe that's optimistic. I don't know, but I think when you really consider what we can do with AI, it becomes almost a more believable number, although still quite big. So I think what we've seen so far, GitHub Copilot, and other obviously AI things, they're like the earliest developments of what is going to be a very significant shift in just the way we work and the way we do things. We're going to see, I think, a big difference within the next 10 years, which is what Goldman Sachs is predicting here. Right? This is sort of what they predict for the next 10 years. On the left is obviously the 7% from global GDP, and on the right, that is, so on the bottom we have the software market. They call it the total available market, which is I think basically how much money there is in a particular market, or how much money there can be in a particular market. And they actually expect GenAI to, it's almost 20% next to the full global software market, which is it's a pretty big number. So, I mean, despite all of this, right, and despite all this hype, LLMs are not always that great, right? Because, you know, there are some examples like GitHub Copilot, where an LLM is, it does really well. It makes a big impact, but it's still, in essence, it's a black box that just does autocomplete very well. Alone, it's very unpredictable. It's massively prone to hallucinations, and the knowledge within it is not up to date. So, with all that in mind, it makes me think, at least, that LLMs are good, but are they 7% of GDP good? I'm not sure. But that being said, there's an entire ecosystem around LLMs, and when we start building with that ecosystem in mind, that kind of changes, in my opinion, on that. I think we can, all of a sudden, we can do a lot more with LLMs and AI. So that ecosystem kind of looks like this. So the LLM is it's the engine, it's the core of that ecosystem, but there's a ton of other things around it as well. All right. So, you know, obviously prompt engineering, we all typically do that with LLMs. It's like the first thing you do. But there's other things. You have conversational memory. That's, you know, you need that if you're building chatbots. External knowledge bases to basically manage the knowledge of your LLM. You have fine tuning. Large language models can execute code. You have evaluation, dialogue flows, detective guardrails, and also agents, which is almost like another layer around LLMs that allows you to sort of work even better with all of these other components. Now, to understand how to use LLMs properly, you kind of need to understand how to use these other components and where everything fits in together. So this is just an example of where LLMs don't work as well. So this is GPT-4, right? GPT-4 is without a doubt the most powerful LLM available to us today. It is, so this is the first version of GPT-4. This is within the OpenAI playground. And I said, okay, how do I use the LLM chain in LangChain, right? And this shows a very obvious issue with these models. Despite this being GPT-4, it tells us that LangChain is a blockchain-based platform that combines AI and language processing, and LLM chain is a token system used by this system. So, I mean, that's wrong, obviously. LangChain is a Python library that we use for GenAI. But the reason that GPT-4 gives us this weird, this hallucination is because it has not been trained on data that contains anything about LangChain. So, that's a big problem, right, with LLMs, right? Especially when we consider this is GPT-4. It's not GPT 3.5, it's not Llama 2. Those models, if they don't contain something within their sort of internal knowledge, they're even more likely to hallucinate and just say things that are completely wrong. So there are a lot of components from that ecosystem that we can use to reduce this, like this level of hallucination, or limit the chance of us hallucinating. But we first need to sort of understand, what is actually going on here, and how we can avoid that. So the problem that we have is that LLMs rely solely on knowledge they've learned during training. Okay, so everything that the LLM knows, it knows from training and nothing else. So they take the training data, they feed that into the LLM, they train it over a very long time with, it costs a lot of compute and a lot of money. And in the end, you almost get like this frozen representation of the world as it was within that training data set. And as for the outside world, anything could happen. The LLM would have no idea, right? It exists completely in isolation of everything else around it. All right, so that's our problem. It doesn't have knowledge of the outside world. It's just frozen in the world that it learned during training. So what we want to do is find a way to add something in the middle that allows the LLM to gain access to knowledge from the outside world. It doesn't necessarily need to be the entire world of knowledge. We don't need to do that, depending on what you're wanting to do. But it does need to, it needs to contain the knowledge that you need for your LLM to do the task that you want it to do. So we need a way of getting that knowledge into the LLM efficiently and at scale. So how do we do that? Well, we want to swap this. So this is the first thing I mentioned. This is the LLM. It's frozen in time. All of the knowledge I gained from its training data is stored literally within the LLM itself. All right, it's called parametric knowledge. That we call it parametric knowledge because that knowledge is stored within the model parameters, right? The weights of the model. That's frozen, right? We can't do anything about that. We can fine tune, but it's expensive. It takes a long time. So we actually want to swap that for something more like this. So we want to add another place of knowledge. Now, one of the most popular ways for doing that is using a vector database. Now, a vector database is useful for many, many reasons, as we'll discuss. But one of those key reasons is the fact that we can just add and delete and update data, which you can't do for the knowledge stored within the parametric knowledge of the LLM. Right? So we add this extra component. This knowledge is fed into the LLM via the prompt. And because we're feeding it in via the prompt, we refer to it as source knowledge. Okay, so that helps us a lot. We can manage the data like we would a normal database. That's pretty cool. But okay, how do we actually feed that external knowledge into the LLM? Like I said, it's via the prompt, but it's not as easy as just throwing everything into the prompt, right? You can try. It depends on how much data you have. If you have maybe like a page or 2 pages of text, you can probably get away with it. Anything more, you're going to run into problems, which might be surprising to a few of you because there's almost like this obsession about context windows with LLMs. And context window, like big context windows can be important, but the problem is that they're very inefficient. So if we look at this graph here, we're seeing, okay, we're fitting, so on the x-axis, we're putting more documents into our context window, more text into our context window. On the y-axis, we have accuracy, or the ability for the LLM to recall some information that was placed within that context window. And you can see as we add more text into the model, into the context window, the ability for it to recall information actually decreases pretty significantly. And there's two links at the bottom here. You'll also get, you can probably Google the paper name Lost in the Middle or the Pinecone article Less is More. But you will also get these slides after the call. So you can just click on them then. But that explains it in with a little more elegance than what I can. But essentially, you can fill up your context window, and your LLM will basically remember what is at the very start of your context and what is at the very end. And everything in the middle is basically hit and miss as to whether the LLM is actually going to see that information and use it correctly in your answer. It's kind of like a person, right? If someone gives me 2 paragraphs of text and then asks me a question, I read it, and then they ask me a question about those 2 paragraphs of text, there's a fairly good chance that I'll be able to answer that question accurately. If someone gives me 20 pages of text, gets me to read it, and then asks me some random facts about those papers of text, I'm probably not going to be able to answer them correctly. And maybe if it's at the end, just like the LLM, and maybe even if it's at the beginning, like the LLM, but if it's somewhere in the middle, there's a good chance it's out of my mind already. So context stuffing is basically it's not a good idea, and we need a better way of going about that. Okay, so yeah, is there a better way? We need to find a way of selectively feeding highly relevant information into our context, not just all information. So a vector database it's a very powerful way of allowing us to do that. So basically, with LLMs, we're talking natural language. A vector database it fits very well with this because it also essentially speaks in natural language, right? It uses what we call semantic search. Semantic search, it is essentially like capturing the meaning, like the human meaning of some text, and encoding that into what we call vector space. So like vectors and sort of like a 2D graph, like you have those points on your graph. Imagine that, but the points in your graph, they're closer together if they represent some text that has a similar human meaning, right? And we can then use that to build this sort of semantic search tool. So with a vector database, we take a user's query, we encode it into this vector space, and then we use that to look for relevant documents and feed that information into our LLM. That whole process as a whole would be called retrieval augmented generation. Okay, so it looks kind of like this. At the top, we have our query. It's like, okay, what makes Llama 2 special? We take it down to the embedding model. That's the yellow diamond there. That embedding model, I think we will talk about them more soon. But that embedding model is the thing that converts your text into the machine readable vectors. We send that vector to Pinecone. Pinecone contains all of our relevant documents that we believe may be useful for our LLM. It's like our connection to the world. And we get a load of relevant context from that. From there, we augment our prompt with those relevant contexts. So that gives us a retrieval augmented query. We take the query and the context and basically just concatenate them. And then we feed that to our LLM. Now, because our LLM now has knowledge of what Llama 2 is, because we retrieved it from Pinecone, it will be able to actually answer the question accurately. Now, I mean, there's obviously just the fact that it can answer a question accurately. That's already a ton better than just using an LLM by itself. But it also gives us, as users and also as developers, it gives us more confidence in what it is providing to us. Like one thing that we see very often on the user side or on the interface side is that we can add citations to the text that we provide. So that's just a way of telling our users, look, this is where this information is coming from. If you're not too sure about the accuracy of this, you can go through and click and prove for yourself that it is actually correct, which it hopefully will be. So that's another sort of benefit, a little side benefit of using RAG. There's a little more confidence in what you're giving people. Okay, so retrieval. Let's talk a little bit more about that. So go into a lot more depth into that little box there. So the embedding model, the query vector, and the vector DB. So before we take the text to our embedding model, we do this process of chunking, right? So chunking is, sorry, I just lost myself here. So chunking is, we take some long text and we basically just split it into smaller chunks. Now, the reason that we do this, I mean, there's a few reasons. So first and foremost, if we took, let's say, 10 pages of text and we embedded them, right? And then we retrieve that during our RAG process and pass that along to our LLM, we have 10 pages of text going into our context window, which doesn't help us, right? It's we haven't solved a problem. We're still feeding too much into our context window. So that's the first reason as to why we want to chunk our text. Another reason is for the embeddings to be accurate, it is usually better to use smaller chunks of text, right? And you can think of it like this. As a person, if you, let's say, I don't know, you had some categories or something of, the meaning behind some text. One of those categories is someone is talking about sports. Another one is someone is talking about AI, right? So you have these different categories of where you want to categorize chunks of text. If someone gives you a 10-page document that talks about many different topics, like where do you, what category do you put that into, right? It becomes very hard when you have a lot of text to define a specific meaning to that text. And the same is true for embedding models, right? If we have a ton of text, that text, it probably contains so much information in there that it basically has many, many different meanings. So it is usually better to reduce the amount of text that you're putting into your embedding model by chunking it and just embedding that smaller segment so that we can basically be more concise with whatever the meaning is before that text. Now, the actual chunk size that you use is going to depend on your use case, right? In some cases, it may, maybe you just want a sentence of text, right? Other use cases, maybe it makes more sense to have a few paragraphs. It really depends. But yeah, it's usually a good idea to do this. If you are going to do this, just in terms of like implementation details, LangChain has many text splitter objects that they're just kind of like the go-to for doing this. So I'd recommend going with something like that. And there's also the idea of using overlap in your chunks. So basically, by using overlap in your chunks, imagine one problem you might find when chunking text is that you might cut a chunk like in the middle of a sentence. You would basically create some rules that you try and avoid doing that, but sometimes maybe it's unavoidable. So let's say you cut the text in the middle of a sentence. That means you're going to lose some context between the first chunk and the second chunk, right? So one way of minimizing the risk of that happening is to add some overlap between those chunks of text, right? So you basically share some text between them, and in that, when you do that, you're less likely to lose any information as you're doing this chunking. So yeah, that's important. And then after that, we go on to the embedding and the embedding and retrieval parts. So traditionally, this is what you do, right? This is sparse vector search or sparse embeddings. The idea here is that you're looking for terms or shared terms between a query and a document, right? And you can kind of see there's definitely limitations in this, right? If you have the query, do any large monkeys come from the jungles of Indonesia? And you have the answer, like this is definitely the answer. Orangutans are native to the forests of Indonesia and Malaysia. There's only one term or one word that overlaps there, which is Indonesia, right? The rest, like you say, large monkeys, which is the apes. So that's kind of wrong anyway, but the meaning is there. So large monkeys / apes should be orangutans, right? But because they are not they're different words, traditional vector search or traditional search wouldn't pick up on that, right? Native and come from, again, it's the same. Rainforests, jungles, there's probably some difference between those two, but in terms of the human meaning here behind the query, that is what they're looking for. But we probably wouldn't return the correct result in this case with traditional search. So that is one of the reasons that we would use semantic search, because when you look at these, the meaning behind them is for a human, it's clear to see that the answer here or the doc answers the query, right? So that's why we use semantic search, which is more aligned to how we would think as humans. So, okay, how would that work? Well, the semantic meaning, you can kind of see how it works here. In the case of bank, with traditional search, bank would just they would be matches, right? With semantic, they would not be, because depending on your embedding model, you'd be looking at the word bank and you'd see that the context around them is different, right? So in that semantic vector space that I mentioned before, those should be very separate within that space. On the other hand, right, we have the sentences at the bottom. They don't share any terms, any words between them, but the meaning is basically the same. So in semantic search, these two sentences would be viewed as being very similar. They'd have a very high proximity, as we can see on the right. All right. So, I mean, how does that actually work? As I kind of mentioned before, we take our sentences. We have the two like yellow highlighted ones. They have the same meaning, right? So you go to your semantic embedding model, and the output from your semantic embedding model should be two vectors that are very close together. The other text that you see there is the capital Texas, USA is Austin, right? With that, again, if you think to the term overlaps, we have capital, we have USA. So, there's some overlap there. But because we're embedding the semantic meaning, the embedding model will identify that actually that's very different to the other things. Now, actually, one thing I should say here is that when you think about the meaning of sentences here, that can vary depending on what you're wanting to do, right? Like in the earlier example where we had the query and the document, like the query about large apes or gray apes, and the document about orangutans, because depending on on what viewpoint you're looking at that in terms of the meaning, you could view those as being very different or very similar, right? If you're viewing it from a sort of pure semantic meaning, that question and the document may be very different, right? Because the question and the document, like one is a document, one is a question, right? So another question that is about something completely unrelated could be viewed as being semantically more similar just for the fact that it's a question. So if you consider semantic meaning in that scenario, then there's a big difference between them. But then you can also look from the question answering viewpoint. And in that viewpoint, the semantic meaning would be very similar, right? Does this answer the question that is being provided? So embedding models, you'll find that different embedding models tend to focus on different aspects of semantic meaning. And then some are just kind of like good all-rounders, which would be, for example, text embedding ARDA002 from OpenAI is like a good sort of all-rounder, which manages to handle like Q&A, also manages to handle like the pure semantic search, and manages to handle most of those scenarios pretty well. So there's always a consideration here of, okay, for your particular use case, which embedding model will work best? And that's something that you just need to investigate and test. Okay, cool. So vector database. So vector database is basically wrapping up all that logic that we just discussed. All right. And it's putting it in a sort of behind a managed database, which just allows us to manage the data and the vectors and stuff that is in there. But also, and perhaps more importantly, it allows us to search more efficiently through that vector space, right? Because there are different ways of doing search within vector space. Some of them are more efficient, less efficient. Some of them are more accurate and less accurate. And if you, for example, use a vector database like Pinecone, what you're getting there is something that's very efficient and also very accurate. All right. So there's good, basically you can do it well and you can do it badly. At least at Pinecone, we think we do it pretty well. And as part of that, doing it well, you also want to be able to search at scale, right? So if you're indexing a lot of data, a lot of these documents, a lot of these vectors, you're going to get to a point quite early on, if you're not doing it right, where you begin to run into issues, right? If you use the standard vector search method it's called exhaustive search, and it's called exhaustive because you say you have your query, you're comparing your query to every single other vector within that vector space. As soon as you get to like 1 million vectors, that means for a single query, you're needing to do 1 million vector comparisons in order to get an answer or to get some responses or context from your vector database. So you don't really want to do that. Instead, you want to do what we call approximate nearest neighbor search, which basically approximates the answer, but to a very high degree of accuracy. And using, if done correctly, again, using that, you can scale up to literally billions of vectors, which at least, I think is pretty cool. So going back to the whole RAG process, we've understood the retrieval and the vector database part. Now we want to go back to the whole, actually here, we want to go back. Okay, we have our relevant context. Now we want to go to the retrieval augmented query, the LLM, and the rest. So this is what that retrieval augmented query may look like. Okay, so where are we? The highlighted yellow bit, that is the original query from the user. Above, we have our instructions. So this is pretty typical that you would see with LLMs and prompts. You have basically some instructions that are telling the LLM how to behave, what it should do, and just instructions on how to, go ahead. And then the bit that we've just added in, the bit that makes this retrieval augmentation, is that context, right? So this context is the information that we've retrieved from our vector database. So we pull that in. That's our external info. That is what we would call the source knowledge that I mentioned earlier. And then at the bottom of all of that, we have what we call like an output indicator. This is LLMs is essentially very good autocomplete engines. So it can be helpful, particularly if you're not using like some big LLM like GPT 3.5 or 4. It can be useful to just give some sort of indicator to the LLM as to how it should begin generating text, right? So that's what we're doing there. And you put all of that together, and what you end up with is this, right? You end up with RAG. So with RAG, there's a few things that that are good, right? Some pros. We get retrieval of highly relevant docs using natural language. So we have that access to the outside world. We can scale it to billions of records, if you do it properly. Again, that is incredibly useful. We have data management like a traditional database. So, there's no more. The LLM is still a black box, but it's less of a black box. We at least know what is actually in there or we know part of what is within the LLM, and we can also manage part of that as well. And we don't need to do context stuffing, which is great. So our recall performance for what is in those prompts will be a lot better. So that is also a pro. But that's not all. There's more to RAG than just what we spoke about. In fact, what we just spoke about is a very small part of RAG. So a chunk size and overlap, actually, I already spoke about that. One thing that I see people use a lot, and it's not necessarily a bad thing, it just depends on what you're wanting to do. But their default retrieval tool, inline chain. I know a lot of us are using LangChain. That's why I put it here. That makes like 3 LLM calls, which is quite a lot and not as many as you actually need to do retrieval. The reason it has that extra LLM call is because it's some summarization, which again, that can be really useful if you're returning a lot of documents. But the idea with RAG is that you don't want to retrieve too many documents. So, depending on your use case here, you may or may not need that. If you don't need that summarization, then I just recommend creating your own little RAG pipeline. But I do also at the same time, I'll just note that I know there are some new retrieval tools or retrieval functions in LangChain that I haven't used yet. So maybe some of them also solve that issue. And then we also need to think about which RAG method is best, right? So all of the RAG stuff that we just spoke about is literally that naive RAG at the top there, right? So it's almost like it's like entry level RAG. There's other ways of doing RAG, which are kind of cool and give us a lot of other things we can do. By the way, I say entry level RAG, that doesn't mean that you shouldn't use it. It has its own pros in many ways, but it also has its cons. So it's more like, you should use these different methods depending on what you're wanting to do, what your requirements are. So I'll just talk very quickly about these other forms of RAG. Okay, we have RAG with agents. So agents, I kind of mentioned at the start, it's almost like having a logic layer around your LLM where it can take multiple steps to think through your question. It can use tools. It can do all these things. Now, agents are really cool. And you can kind of see here what that might look like. So in this, I think this is actual code and actual output. So at the top, we have this conversational agent. And I say, okay, can you tell me about large language models? And it enters this chain of internal dialogue where it's thinking through, what you've asked about, right? And it thinks, okay, large language models. Okay, in order for me to answer this question, I should search, right? I should find some information about them, right? So it has this you can see it has this thought and it has action and it's a search, right? That search thing there is a tool that the agent has access to. Now, tools that agents can have access to can vary, right? Here, I'm kind of showing, you have search at the top. You also have a calculator. They can use calculators and they can execute code, right? And actually, they can basically run anything. They can do a lot of things. So that's a tool that we've made available to our agent. And the action input that it's doing here is large language models. So it's looking at your query and it's saying, okay, I need to search for large language models. That would run our like retrieval tool, right? So that whole kind of like the RAG thing we just saw, it's very similar in the structure here, but we've added a layer before deciding to use RAG, where the agent is allowed to decide whether it needs to or whether not to. And then it gets its response, and then it has this sort of final answer that it returns to us. All right. So that can be really useful, particularly if you have conversational memory, right? Because in the naive method that we spoke about, we're just taking the user's query and we're feeding it into like a RAG pipeline. If you're having a conversation with your LLM, you know, is your most recent message always going to contain the information that you want to like search for? Probably not, right? So like in this example here, I'm asking about LangChain, and then the agent tells me about LangChain. So this is on the left. It's saying, okay, LangChain is this Python framework developed by LangChain AI. And then I'm asking, okay, what information do you have about the company? If I just use the naive RAG approach here, it's going to then take that interesting, what information do you have about the company, embed that and search with that, which doesn't tell us anything, right? That's not what we're asking about. We're asking about LangChain AI. Here we're embedding this, which doesn't contain anything, right? That's not what we want to know. So on the left, if we have conversational memory with an agent and we have a connection to our RAG tool, it will give us a good answer. On the right, if we don't have conversational history, and this would be the same as if we use that naive RAG approach, it doesn't know what we're talking about, right? Or at least it won't know what to search for. Okay. So agents and RAG, it's really good because we can specialize query for search. We can use multiple tools or retrieval steps. We can only search when required, but there are issues with agents. Calling an LLM takes a long time, right? And essentially, you're making at least 2 LLM calls if you use an agent with RAG, which is one more than you would have to use with the naive RAG approach. So it's going to be slower because you're making more of those LLM calls. And it's also more expensive, right? You're paying OpenAI for every, where are we? But if you're paying OpenAI for every token used, you're using more tokens. Now you're paying them more, right? So again, it's a trade-off, whether you want faster and cheaper, or you want slightly slower, but more powerful, right? When I say slower, if you have a good internet connection, this shouldn't, like one query with RAG, if it just decides to do a search, if the agent decides to search and give you the response, and that's your final answer, so it's like 4 to 5 seconds if you're using GPT 3.5, right? So it's not like it's that long in reality, but it's a little slower. And then, okay, so the other one, this is RAG with guardrails, and this is the one I have less experience with. I've implemented it and tested it. It seems pretty cool, but it's not the sort of thing that I've seen particularly. It's not very widespread. So the idea of RAG with guardrails is it's almost in between, right? It's in between the RAG with agents and the sort of naive RAG. So on the left, we're essentially defining what should trigger a search, or what should even trigger tool usage, right? So we have these, we call them utterances. It's just like an example query, right? So on one, the top left one, the user is asking some political question, right? So it's almost like we're defining a set of examples that would be classed as fitting into that category. On the bottom, we have the user is asking about LLMs, right? And then we give a few examples as to what would define a question about LLMs. We then feed all those into an embedding model, and we get we get those representations within our semantic vector space. Right, we're not encoding a ton of things here, just enough to kind of cover our bases on what we think would be categorized within each one of these canonical forms. The canonical form is like the user as political or the user as LLM. Now, what we can do with this is we can decide on what tools to use based on semantic similarity. So rather than deciding like we did with an agent with an LLM call, we decide with semantic similarity. And the difference there is obviously speed, right? If you do a semantic search, the response time you get there, or the time it takes to make a decision, is almost instant. It's super quick. With an LLM, you're going to be waiting a few seconds. So in this user query, we're going to say, okay, are there any government-built language models? So it's almost in between those two categories we made before, but it's very clearly asking about LLMs. And if we've defined our vector space well with those example questions, we should find that the most similar group of utterances will trigger or will belong to the user ask LLM canonical form. And if it does that, we can then trigger the search, right? We can trigger search for LLMs. So that's just another alternative approach that you can use for implementing RAG. So there is, at least as far as I'm aware, and I'm sure there are probably other approaches to it as well, they're the three sort of methods that you may want to use at the moment. So yeah, pros and cons for the guardrails idea, and I think this should say RAG and guardrails. Oh, maybe okay, but basically you only search when required. It allows you to make decisions on tool usage, and using guardrails is much faster than agents. But again, there's still some issues. Like if you need specialized queries that include like metadata and stuff, you still need an LLM to generate those, and it's just not as robust as an agent, right? But it's still pretty good. So, I mean, that's it. Just to conclude very quickly, we've been talking quite a lot. LLMs alone are pretty limited, but with this sort of ecosystem, we can get around that quite a bit. Prompt engineering is typically our starting point, and then with RAG, we are able to get a manageable database of knowledge input into our LLM, right? So it's almost like we add a little bit of a database onto our LLM's brain. You can think of it like that. And there's also many ways that we can do RAG, and you decide on which one based on your use case. So yeah, so if you want to get started, we have we have a LangChain ebook, and we also have a lot of other articles talking about RAG and LLMs and everything else in our learning center. So that would be at pinecone.io/learn. And yeah, you can follow us on YouTube and Twitter or X, depending on which one you want to call it. And yeah, that's it for me. I'll pass over to Amanda for some questions.
Yes, great job, James. And we have such an interesting and cool crew who's joining us today. If you take a look at the chat, there's some really interesting projects happening out there. So thank you to all of you who joined. Now let's dive into some questions. We only have a little bit of time, so I'm going to skip around a bit. Brian wants to know, what's the best way to handle irrelevant results in the top K? Is there a good way to pre-filter them before handing them to the LLM?
Yeah, definitely. So one thing that I've used a lot is re-ranking. So one way that I like to do it, it's super easy, is Cohere. They have a re-ranking model. So basically what you would do in that case is let's say you take 100 as your top K from Pinecone, right? And there's probably a pretty decent chance that you have some relevant results in there, but you don't want to pass in those 100 documents to Pinecone, because then you're context stuffing and you've got too much stuff in your context. So instead, what you might want to do in that scenario is you use like Cohere or another re-ranking model to basically do like a second look at what you have, right? And that will just re-rank all of your context. And it's a much more you're using a large language model to decide, which rank these should be using, which is much slower than if you were using if you're just using vector search over many of your contexts. But because you're just doing it over 100 contexts, it's actually very quick. So I don't know what the timing is there, but it's very quick. You wouldn't usually notice it in your queries. So you get to re-rank everything. It's more powerful, and therefore within the top 3, you're probably going to get much more relevant results if you go for that approach.
Can you talk about some best practices for securing LLM-based app for production deployment?
Securing, I'm not really sure on I'm not really sure on securing. It depends on, I suppose it kind of depends on in what way, like what way you're securing it. But yeah, it's more of like so it's probably more of a DevOps question, which I don't really have experience on.
Fair. What are some methods to evaluate optimal chunk size? And chunking is always, a big point of conversation. I feel like we need to do just an entire webinar on chunking, by the way, for vectors inserted. For example, subject matter text for a SME chatbot.
Yeah. So yeah, I mean, chunking is an interesting question, because there's not. It's very use case, and yeah, it's very use case dependent and even model dependent, right? If you're, let's say you're using, right, if you're using sentence transformers, they're like open source alternatives to like OpenAI. If you're using some of the older sentence transformers, you're actually limited in how much text you can put in there. So you should use smaller chunk sizes. Let's assume that most of us are probably using OpenAI's embedding models, which, by the way, is not, it's not actually the top embedding model. So it's definitely worth, if you are using those, to look into other embedding models. But let's assume we're all using that. The embedding, you can put a lot into that embedding model. It's fine. But like I said, you don't want to put in too much because it's going to cause issues down the line with your LLM, particularly if you're using open source LLMs, which tend to have smaller context windows. But also even for GPT-4, GPT-3.5. So you want to minimize your chunks, but you still want to capture enough information that you're capturing good information there. So my sort of rule of thumb, and this is just a rule of thumb, it really depends on the data and everything, is that I will go between 300 to 500 tokens, right? So token, you can look, if you're using OpenAI embedding models, you can look at take token, which is a tokenizer, to count how many tokens you've got there. But I tend to find 300 to 500 works well, because you're avoiding context stuffing, and you're usually capturing enough meaning within those chunks that your embeddings are effective. But again, that's a very broad stroke. Like it's going to depend. I would say beyond that rule of thumb, what I will tend to do is I'll chunk into those chunk sizes, and then I'm going to actually look, like I'm just going to look at my chunks and see, do they make sense to me as a human being? If they do, then they will probably make sense to the embedding model as well.
How can I better prompt an LLM with context retrieved via a vector DB?
How can you better prompt a LLM with context retrieved? Okay. So, okay. So, like the basically the instructions that you're using, I think that is the question. Well, one thing, obviously, like I mentioned, is that don't put too much in there, right? And that applies to everything, right? You basically, this is just like general prompt engineering, right? Don't over don't put too much in there. You want to get all of the information in there, but you want it as concisely as possible, because otherwise you're just going to confuse the LLM. right? You want to be as concise as possible. It's like with a person, right? If you want to teach them something, you want to be super concise, but you also don't want to be missing information, right? So just that is like generally that's what you should do. And then specifically to RAG, you want to have you have followed the sort of structure that I showed, where you have your instructions at the top, then you have your context, and then you have your query. Your instructions should be, like I said, concise, and you should say, okay, using the context that we provided below, answer the question, the query that is below. One thing that you can also add in there to like reduce the chances of hallucination is be very, very specific to or explain very obviously that the LLM should not answer a question unless the answer to that question is provided within the context. Right? That's like the overly careful approach that you can do. You can be a little bit, a little bit softer on it, right? You can say, okay, answer based on this information or something like that. If you don't want to be too strict, if you do still want it to use its own parametric knowledge rather than just the source knowledge. So yeah, it depends on what you're wanting to do. But I almost always add in something like use the context to answer the question. And if you do not know the answer, say, I don't know, right? So it doesn't hallucinate too much.
Great. So how can vector databases and embeddings be used for data that isn't words, but rather numbers that are related to things like sales data?
The message here. So how can vector databases and embeddings be used for data that isn't words, but rather numbers that are related to things like sales data? So basically, if the embedding model has been trained on that sort of information, then you can use it. But it depends on whether your embedding model has been trained on that data. It's really just going to depend on what it's seen before. I would say sales data, they probably like a model like OpenAI's embedding model. It's probably I would imagine it's probably seen a little bit, so it probably has some little bit of like knowledge there, but probably not a ton. So at least on the semantic search, a dense embedding model, which is what sort of model that is, you just want to look for the right one that has been trained on more of that sort of data. I don't know if there are models out there that have been. One thing that you can add into the mix to improve that ability to sort of work with more niche domains or niche data sets like that is actually to add, I mentioned traditional search earlier. You can actually use the embedding models that you would use in traditional search alongside semantic search. All right, so it's something we offer at Pinecone is hybrid search. And basically what you're doing with hybrid search is you're taking your sparse embeddings, your sparse vector, and your dense vector, which is the semantic vector. You search with both, and then the results you return will be based on the relevancy according to both of those types of search, both of those vectors. And that sparse embedding method, although it doesn't work so well with semantics, it actually does work very well when you have things like that, like sales data that has very specific terms and keywords or even numbers. It can work better in that scenario, right? So you can use both in that case.
So we're nearly at time, but I wanted to end on this question from Daniel. Can you discuss some examples of where RAG might not be appropriate?
Mm-hmm. Yeah. So where would RAG not be appropriate? It depends again on what you're wanting to do, right? So, and these I said these examples are not even that great examples where not to use RAG, because you can still use RAG in some of those. But let's say like creative writing, right? You want your LLM to basically help you get past writer's block. maybe in that case, you don't really need to use retrieval augmentation because, okay, what information are you retrieving that's going to help your LLM with what you're wanting to do? Or another one is maybe you want your LLM to take on the tone of voice of your company, right? One possible way that you could do that is using RAG, right? That is like an easy way of doing it. Another alternative way of doing it would possibly be by fine-tuning your model, right? So fine-tuning is typically better when you want the model to basically take on more of a personality that you were specified, or a sort of tone of voice, right? So in that scenario, rather than using RAG, you might want to use fine-tuning. But I will also say that a lot of the time, most use cases, not all, but most use cases tend to benefit from RAG. And actually, if you're looking at fine tuning as well, they tend to benefit from both more than just one or the other. Yeah, I think that probably can't really think of any other examples where you wouldn't use RAG. I mean, there are plenty, but you should know basically when you're building your app, your tool, if you're not needing documents from a particular database, or you're not needing up-to-date information, then possibly you don't need to use RAG, right?
Okay, great. I see all that's going on in the chat, guys. We'll definitely create a group. But yeah, on that note, we're gonna close out. James, thank you so much for the session, and thank you to everybody who attended. This has been a super unique and exciting group of people, so we really appreciate your participation and your engagement. Yeah, join us at our next event and give us lots of feedback, especially from this group. I want to hear your feedback and what you would like to see in the future. So thanks all. Have a good one.
Thanks all. See you later. Bye.